Jai to all of you. I am Dr. Ritish Kumar, Assistant Professor, Department of Electronics Communication Engineering, Ajay Kumarga Engineering College, Ghaziabad. Today I am giving the lecture on the topic of different types of antennas. The subject name is antenna and wave propagation, and subject code is BEC 603. So in this lecture, we will mainly study about the different kind of antennas such as horizontal antennas, vertical antennas, Yagiyoda antennas, etc. So we will study in the further slides. Before starting the topic, first we need to look at the syllabus of the university, which is which is uh, which is which has 5 units, and this topic lies in the unit number 4. As you can see, this is the unit name is antenna design, where you can see different kind of electric dipole, short dipole, electric fields of the dipoles, array of the dipoles, and at last you can see there is a kind of different kind of antennas such as horizontal antennas we will study, vertical antennas above the ground plane, Yagiyoda antennas. These kind of antenna we will study in this lecture. So this is unit number 4, and the recommended books, if I say the textbook, then I recommend the book John JD Cross. The title of the book is Antenna and Wave Propagation. If I talk the reference book, then I will refer the book C.A. Balanis. The title of the book is Antenna Theory, Analysis and Design, and the publisher is John Billy. So let's begin the topic: horizontal antenna above the ground plane. So horizontal antenna, as name suggested, it places above the ground plane horizontally with respect to the ground. Field pattern is so what will happen there, if I say what will be the effect on the field at some distant point P. So field pattern is much affected by the reflection from the ground. The reason is that ground is considered as a reflecting surface, because ground is nothing but a perfecting reflecting surface, as I can say. And consider the horizontal lambda by 2 antenna at a height h above the ground plane of infinite extent, as shown in the figure. When the antenna is grounded or ungrounded but close to earth, its directional characteristics are altered. As you can see in the figure, this is a ground plane, and here the antenna is placed horizontally with respect to the ground plane. So at some certain height h, as the statement has been written over here. So if I this is a kind of you can see this is a image, because ground is nothing but a perfect conducting material, or we can say perfect reflecting surface. Or if you correlate the things with the image theory, you can make the same antenna just below the height h. It's similar height h below the ground plane, and then you can see this is an image of the antenna. If the because of the reflecting surface, this current, if you correlate the things with the image theory, then this direction would be reversed because of the image theory. And you can see here because this is a you can treat this dipole antenna as a source element. You can see here this is a source element, antenna 1 and antenna 2. And if you forget this part below the ground plane, then at some distance point P, there are two paths to travel the wave. Either it can move from antenna element 1 to the direct point P, and there could be possibility to have the reflection from reflecting surface, that is nothing but the ground plane. There is a possibility to have the reflected wave. So at some distance point P, there could be possibility to have a direct wave or reflected wave. So you need to find, if somebody asks what should be the field intensity at point P, so you will have two component, a direct component of electric field or indirect component, that is reflected component of the electric field. So you need to find the resultant electric field, that is the vector summation or vector subtraction of the electric field intensity of both component, direct or reflected wave. So this is the concept of image theory here, right? So uh, so as the statement is written, the third statement, the radiation directed towards the earth is reflected, thus the total field in any direction will be vector sum of direct or reflected radiation from the ground, that I already discussed from the figure as well. So you can see here, after due to the you can make the image theory concept here, and you can make this same antenna below the ground plane, and you can image the antenna element 2, which is a similar height as compare as it has above the ground plane, that is h. So so uh, so you can say this reflected wave comes from this imaginary antenna element 2, which is comes from, directly from this antenna element 2 to the distance point P. I hope this direct or indirect or reflected wave concept is clear to all of you. Why the reflected wave is happening here? Because of the ground plane is nothing but a perfect reflecting surface. You can treat it. So here, as I told you in the last slide, the resultant field is made up of direct or reflected wave. The image antenna is being the virtual source of the reflected wave. Here, the ground is assumed to be perfectly conducting, so the tangential component of the electric field must vanish at the surface. Therefore, the reflected wave must suffer a phase change of 180 degree. So in the further slides, we will study how we can calculate the electric field intensity at a particular distance point at P. So this is the ground effect over the horizontal antenna. So you can see this is nothing but a dipole antenna, and you can have the current distribution in this form. So because of the 180 degree phase shift in between the reflected wave and direct wave, so this due to the from the image theory concept, this flow of current is reverse as have in the AA dash. You can see here, this is the direction of current, and this is the direction of current below this antenna image element 2. So you can see this is this current distribution is 180 degree phase shift with each other. So this is the physically antenna exist over a ground plane, and this BV dash is the imaginary antenna or virtual antenna which physically does not exist, but you can image it below the ground plane. That's why we call this is a image theory concept here. So you can have two dipoles. You can treat it as a two dipole, A dash and BEV dash, and at certain point P you have to find out the electric field intensity. So you can see if the direct ray path is from A dash is in this direction, and from BB dash in this direction. So first you need to find out the travel path difference from A dash and BB dash up to the point P. So you can see this is the path difference which is traveled more compared to the this path travel distance. So this is nothing but this is distance h, this is distance h, and if you make it the angle is phi, so this distance is nothing but 2 times of cos, 2 times of h cos phi, right? I hope this one is clear to all of. So this the wave coming from the BV dash is travel more more about 2h cos phi. So this is a path difference. Then you can able to find out the phase difference. So phase difference you can calculate with the help of this formula, that is nothing but 2 pi by lambda into path difference, right? So path difference is the path difference is 2h cos phi. And if I ask that what should be the total path difference if you consider this figure, so total path difference is the path difference traveled by this wave from BB dash, and 180 degree comes into the picture. This is beta is equal to 180 degree because you are treating the ground plane as a perfect reflecting surface. So, the total path difference is represented by alpha is equal to beta upon 2 pi by lambda 2h cos phi. So, this one is the travel path difference, and beta is due to the perfect ground plane. Or for perfect ground plane, beta should be 180 degree. So this one is the total phase difference or total phase difference, that is represented by alpha is equal to beta plus 2 pi by lambda 2h cos phi. So finally need to calculate the resultant electric field at point P, which is given by EP square is equal to EA square plus EB square plus 2 EA cos theta. Right. So EA is the electric field intensity due to the direct wave, and EB is the electric field intensity due to the indirect wave, that is reflecting waves from the ground plane. I hope this resultant field equations clear to all of you. Twice EA EB cos theta, and this is nothing but is the phase difference, right? So you have to write theta is equal to beta plus 2 pi by lambda 2s cos phi. Then the mathematical section you have to do to find the electric field intensity. So you can see here, if you take EA is equal to EB is equal to EA, then you can take it, EA comes out from the square root of, so EA is equal to 2 plus 2 cos beta plus 2 pi by lambda 2s cos phi. Then after doing some mathematical calculations, you will get at last 2a cos beta by 2 plus 2 pi h lambda cos phi, where for the perfect reflecting ground plane, beta should be 180 degree. You have to put here. So beta is equal to 180 degree. 180 divided by 2 is 90 degree plus 2 pi h upon lambda cos phi, and cos 90 pi by 2 plus theta is equal to minus sin theta. That's why this resultant field EP is equal to minus 2 EA sin 2 pi s 2 pi by lambda h cos phi. So if you see into the picture that theta is equal to 90 minus phi is equal to 90 minus theta. So here phi is equal to 90 minus theta you have to put here. So cos 90 minus theta is sin theta. Then finally you will get the resultant electric field due to the horizontally placed antenna above the ground plane is given by EP is equal to minus 2 EA sin 2 pi by lambda s sin theta. So you can see, the for the horizontally placed antenna above the ground plane, the field variation is sinusoidal by nature. Uh, so this one is the electric field, resultant electric field, which we'll get after some certain mathematical calculations. So the next part is the vertical antenna above the ground plate. Similarly, we have place a antenna vertically with respect to the ground, as we have in the horizontally antenna, which is similar kind of thing we have to do in the vertical antenna. So again you have to apply the image method concept here similarly, but only the things you need to look at here, on the direction of the current would be same in both the antennas, either physically exist antenna or imaginary antenna, that is virtual antenna. The direction of current is similarly from upward direction. So similarly you have to calculate the total part phase difference. For to calculate the phase difference, first you need to find out the part difference. So this one is the part difference. This is twice L cos phi. Similarly, as we have done in the horizontally placed antenna, here you need to find a total phase difference is 2 pi by lambda cross part difference that you need to do. Similarly, but in the previously we have for the horizontally case, beta is equal to 180 degree. But in the case of vertically placed antenna, for vertically antenna, or this one is for horizontally placed one. So similarly you have to apply the resultant electric field equation, that is square root of EA square plus EB square plus twice EA EB cos phase difference, right? So this is the EA is the electric field intensity due to the direct ray, EB is the electric field intensity due to the reflected ray or reflected wave, and resultant electric fields you can get with the help of this equation. So after putting the value of phase difference, you will get the electric field equation. Resultant electric field equation is twice EA cos 2 pi by lambda L sin theta. You can see for the vertically placed antenna, the field variation is cosine by nature, while in the case of horizontally placed antenna, it would be a um, variation like sinusoidal like variation. The next topic is the Yagi-Uda antenna. So Yagi-Uda antenna is a most commonly used type of antenna for TV receptions over last few decades. It's the most popular and easy to use type of antenna with better performance, which is famous for its high gain and directivity. So the operating range of frequency of the Yagi-Uda antenna is lying between 30 megahertz to 3 gigahertz, which belongs to the very high frequency band or ultra high frequency band. So as name suggested, Yagi-Uda antenna is very famous kind of antenna. So first you need to look what kind of structure it has. So this is a kind of Yagi-Uda antenna. So you can look at it here. This is a it has mainly three elements. First one is the main element. This one is called the main element as well. These elements are known as 1, 2, 3, 4, 5, 6 are known as director, while the back element, that is called the reflector. So finally we can say the Yagi-Uda antenna has three elements such as main element, also called as driven element, directors and reflectors. So if you make it the front or top view, you will have this kind of figure as well. So here we need to understand what should be the role of driven element, directors and reflectors. So driven element here is all the types of elements are the dipole kind of elements here. So the main element or driven element is called the main element, while other element is called the parasitic elements, because there is no direct connections of the power to the other elements, right? So the role of the reflector, as name suggested, it reflect the total backward power in the forward directions, right? So reflector is designed in such a way which is slightly larger compared to the dipole main element, which reflects the electromagnetic radiation towards the forward direction, while the directors enhance the radiation in the forward direction. So the functioning of reflector and directors are complementary by nature, we can say. So director will use to enhance the directivity or gain of the antenna in a particular direction, while the reflector is used to suppress the radiation in the backward directions. So as you can see in the figure, the size of the reflector is bigger compared to the main element, while the director is smaller compared to the main element. So this is the functioning of the reflector and director related to the main elements. So and what should be the size of the uh, reflector and directors as compared to the main element? So you can see here the length of the successive directors is reduced by 2.5%. So and uh, if you design this Yagi-Uda antenna, so some parameters are required, comes into in your mind, that is the spacing between the directors and the spacing between the reflector with respect to the main radiator is an important design parameter to decide the directivity of the antenna. So these are the design parameter that you need to focus. The first one is the length of the successive director reduced by 2.5%. Spacing between the reflector and dipole is 0.25 lambda, and spacing between the directors and dipole 0.13 lambda. Spacing between directors and directors 0.13 lambda as well. So the Yagi-Uda antenna is a kind of directional antenna because it has a directional radiation pattern. That's why we call it has a highly directive antenna. So these are the referred book, as I told you in the first slide. So I hope these all the topics of different kind of antennas. The first one is the horizontally placed antenna above the ground plane, vertically placed antenna above the ground plane, and Yagi-Uda antenna concepts are clear to all of you. Thank you everyone.